welcome to the next oral session, which is on perception. So robots have to perceive the world before they can start learning from that data. So that's what we're going to be listening to and talking about today. We've got papers on vision for locomotion, we've got autoencoders, we've got tactile sensing, we've got it all. It's going to be amazing. So we're going to start off with the first talk now. And the first talk is graph inverse reinforcement learning from diverse videos, which will be presented by Satish Kumar. So whenever you're ready, Satish, over to you.
Hello, everyone. This is Satish Kumar, and today I'm excited to present our work, Graph Inverse Reinforcement Learning from Diverse Videos. This is a joint work with Jonathan Zamora, Nicholas Sasson, Rishabh Jangir, and Xiaolong Wang. Sorry about that. Here on the left, you can see a set of human demonstrations, and on the right, you can see the same task being performed with a real robot. Our approach, GraphIRL, takes these human demonstrations and learns a reward in a self-supervised manner. It then uses the learned reward to solve the task with a real robot. We showed that with as low as 16 videos, we can solve the task in the real world. So we know that reinforcement learning works by maximizing reward functions, but how are these reward functions usually obtained? Well, usually these reward functions are obtained by researchers manually doing a lot of trial and error, and sometimes these reward functions end up being very complex. As an example, you can see the reward functions for some of the tasks in the MetaWorld paper. So the process of designing reward functions is complex and can be very time-consuming. So in this work, we asked the question whether we can learn reward functions directly from third-person videos. The framework that we explore is as follows. We first collect video demonstrations of experts. We then learn a reward function in a self-supervised manner from these videos. We then use reinforcement learning to learn a policy in simulation using a learned reward. And finally, we deploy the learned policy with a real robot. The proposed framework has several benefits. First, it substantially increases the scalability of the learning pipeline because it eases up the data collection process, as it is much more easier to collect human demos than doing robot teleoperation. Finally, it introduces a unified pipeline where you could effectively collect data for hundreds of tasks and solve them directly using GraphIRL. Learning from third-person videos is challenging, mainly due to the problem of learning correspondence. If you consider that this door opening task, then two agents could have completely different ways of solving the task. Secondly, even if we could manually define these correspondence for different agents, there might be multiple ways in which an agent could solve the task depending upon the situation. Finally, the collected video demonstration might be visually completely different from the robotic environment where we want to solve the task. This large domain gap makes it difficult for the learning algorithm to generalize from the demonstrations to the robotic environment. The key insight of this work is that despite large variance in videos, the underlying scene structures remain largely similar for manipulation tasks. To understand this, let's see the videos considered in this work. Now let's try to visualize these videos in a more abstract space where each object is represented as a node in a graph and the graph is fully connected. As you can see on your right, even though the original videos exhibit great diversity, the underlying scene structure is very similar for each of the tasks considered. So we use this insight and work on these object representations in our work instead of using pixels directly. Now I'll go over the approach in a bit more detail. Given video demonstrations, we first extract object bounding boxes. We then we then create a graph abstraction by representing each object as a node and making the graph fully connected. We then pass this through a graph-based network. In this work, we use spatial interaction networks, but we could also have used other popular approaches such as graph convolutional networks. This module allows us to model interaction of objects with each other. After obtaining the embeddings, we train using a temporal alignment loss. In this work, we consider temporal cycle consistency, which maximizes one-to-one global correspondence in order to learn alignment. By optimizing for alignment, we learn an embedding space which is temporally disentangled and task-specific. Once we've trained the network for alignment, we can extract the reward as follows. We first compute a representative goal frame embedding by taking the goal frame embedding for each of the video in the demonstrations and then taking its average. Then when we are doing reinforcement learning, we take the current observation, pass it through trained spatial interaction networks to obtain an embedding, and the reward is then defined as the negative distance between the current observation embedding and the representative goal frame embedding. Now I'll go over our results. We evaluate GraphIRL on 4 tasks. These tasks include the simulated benchmark of sweep to top and 3 robot manipulation tasks of reach, push, and peg in box. On robot manipulation, we note that GraphIRL substantially outperforms vision-based baselines by up to 40%. This is because vision-based baselines fail to generalize to the simulated environment due to a large domain gap. In this case, the domain gap is obtained due to the difference between the human data and the simulated environment considered. We also note that, interestingly, GraphIRL outperforms the manually defined environment reward by 30% on push. This is because the environment reward forces the policy to get as close to the goal as possible, as fast as possible. Whereas our learned reward gives higher reward for precision. Therefore, it encourages the learned policy to be more precise at the cost of being slower, just as done in the human demonstrations. This behavior allows GraphIRL to get higher success rate. We also evaluate on the XMagical benchmark, where we notice a similar trend with GraphIRL outperforming vision-based baselines by up to 40%. Now I'll go over the real robot experiments. We conduct real robot experiments with push, reach, and peg in box. Here, you can see the state-of-the-art vision-based method, CrossIRL on the left, and on the right, you can see our approach, GraphIRL. And at the bottom, you can see the success rate, which is the average success rate on our real-world trials. Here as well, just as in simulation, GraphIRL substantially outperforms CrossIRL. One key property of our work is that we are learning goal condition policies. Therefore, our configuration of goal and objects can change, and it can be substantially different from the demonstrations that we see. This is very different from the typical imitation learning works, in which you follow trajectories of experts as is. We also evaluate on peg in box. On peg in box as well, we outperform CrossIRL by more than 40%. One key property of this work is that we do not use any external reward whatsoever. The reinforcement learning trained here is solely based on the reward that is learned from the videos. Now I'll discuss the limitations of the work. First, we need expert human demonstrations for this to work. Even though collecting human demonstrations is much more easier than robot demonstrations, but it is a limitation nonetheless. We also need object bounding boxes of demonstrations, which might not be available in all cases. Also, the abstraction that we do results in a loss of information, which might be useful for some tasks which require fine-grained reasoning. To conclude, we propose temporal alignment using object graph representation for inverse reinforcement learning. This is one of the first work to practically demonstrate a pipeline where you learn reward functions directly from real-world videos. You then use that reward to learn a policy in simulation, and then finally you deploy the policy back in the real world. We note that we substantially outperform previous reward learning approaches on 4 manipulation tasks in simulation as well as real.
Okay, are there any questions from the audience? Yes.
So I'm wondering, thank you. I'm wondering which kinds of features you use in the graph, like both in the nodes and in the edges, because I guess you embed this into some embedding space. So what would you encode in there? And also, why do you use a fully connected graph instead of a sparse one? Because I guess interactions don't have to be between all pairs of objects.
Okay. Thank you for the question. Just let me repeat the question. So the question is regarding the features that we use in the graph abstraction that we create, and why we use fully connected graphs. So the features that we have used in our paper are the 2D spatial locations, so the 2D bounding boxes, so 4 points for that. And then we also use pairwise distances, so distance of each object with all of the other objects in the scene. And then regarding your question about why we do fully connected graphs, this is because we want to have like the simplest instantiation of the scene graph. Because if you get into how you exactly create a scene graph, then it again becomes a scenario where you're manually trying to design the scene graph based on the task. And we wanted to avoid that.
Okay, thank you. And one additional question, why don't you use semantics in the graph as well? Like since you have bounding boxes from an object detector, you might be able to use the class type as well.
Yeah, actually we do use the class type.
All right, thanks.
Okay, that's all we have time for, I'm afraid. So thank you very much, Satish. Okay, so the next talk is Midas Touch, Monte Carlo inference over distributions across sliding touch. And it's going to be presented by Sudarshan Suresh. Okay, over to you, Sudarshan.
All right. Okay. Hi, everyone. I'm Sudarshan, a PhD student at Carnegie Mellon, and I'll be presenting on our work on Midas Touch. This work is in collaboration with Zealand C and Michael Case, my advisor at CMU, along with Stuart Anderson and Mustafa Mukaddam at Meta AI. So the TLDR of this is, given a stream of posed tactile data from a tactile sensor on a robot finger, can we figure out where we are on the surface of an object that we're operating on? So for example, look at this video stream over here, look at the images that we get, can we try to resolve where we are? So it's like a Where's Waldo of a tactile sensor problem. For a sneak peek into what the system can achieve, consider the case of this robot finger with vision-based touch interacting with this object. On the left over here, we have the visual stream of what I'm doing. We're not really using vision here, we're using the tactile data. And we're looking at the pose error over time. So we first start out with a very uninformative prior on where the particles are, but as we get knowledge from salient features and geometries, we can quickly reduce uncertainties of where we are on this object. And the inputs to this pipeline are the tactile images that we get, the noisy sensor poses or odometry that you can think about that are usually obtained from robot kinematics that you have with the robot finger. So at a high level, what Midas Touch does is it uses 3D surface geometry that you get from a tactile sensor. It compactly summarizes these into tactile embeddings. And we can use this to disambiguate over time with just a conventional particle filter. The motivation for this is that robotics researchers are not averse to contact anymore. In fact, the community is doing pick and place. They're not just doing pick and place, they're sliding, they're grasping, they're pushing, bumping, gating, and reorienting objects. And there's a large amount of information at the distal end of these robot arms that is being underutilized, in my opinion. Getting this finger object relative pose is important for essentially state-based policies, controllers, and downstream planners. And during interaction, vision might not give you the full picture just because of occlusion. Incorporating touch can bolster the performance in a manipulation stack for household and warehouse environments you can think about. And to reinforce this, over the past decade, robotics has been dominated by tactile sensing solutions that are specifically designed to maximize the amount of information that you get at the distal end of a robot arm. The geometries that we perceive can serve as valuable information for a pose estimation or a place recognition problem on these objects. For example, if you sense the edge while you're operating with a mug, you can find out that you're on the lip of the mug. And any human can reasonably do this. And the last thing that opens it up is that tactile simulators like Tacto or Taxim allow us to generate these large corpuses of interaction data. And this enables both prototyping and learning observation models that we can transfer to the real world. Our insight here is that tactile perception can be viewed through the lens of an embodied AI or a SLAM problem, where the robot proprioception here gives us odometry just as encoders do for a mobile robot. Visual measurements can be derived from a tactile sensor now. And finally, the ground truth models that we can learn from simulation we can use to learn from simulation, and we can even use to benchmark these problems. So starting out, given this finger object interaction and the resulting tactile stream, which are images, the first step that we have here is deriving these tactile geometries or salient geometries from images, essentially an image to 3D problem. Vision-based tactile sensors perceive these contact geometries as images, and we leverage the success of supervised learning methods in monocular depth estimation, for example, to extend these towards tactile images over here. So in our case, what we do is we have a large set of objects that we generate, and we densely sample poses along with the resulting images and height maps, which gives us a supervised learning problem. And here are some examples that we can see that purely trained through simulation. We can generate pretty decent reconstructions just from these digit images that we get of salient geometries, which forms the first part of this pipeline. And once we have this 3D signal, what we want to do is condense this point cloud into a compact embedding that we can use for a place recognition problem per se. So what we want is, if we have similar geometric features like edges, we'd want to get a latent embedding that corresponds to a pretty good cosine distance between them. So we look towards like point cloud retrieval problems in LiDAR for matching these. So in our case, what we end up doing is doing sparse 3D convolution over the point cloud to generate a 256-dimensional embedding. But you could also use something like PointNet, for example. And once interestingly, we just use these pre-trained models that we get from LiDAR data and just fine tune it with the tactile simulation data that we get to sort of get these embeddings that we can match up. And to sort of visualize that, here we have the TSNA color maps of these embeddings when we densely sample these on these objects. So for example, 2 edges should give us similar hues of colors in this representation. And when we query a given point, we see the other highest codebook scores that match up pretty well in the orientation and the geometry of what we want to see. So when we look across the board of all of these objects, we can see that we can delineate local geometries. So edges on the sugar box, for example, the sharp edges of the scissors, and even the threads of the baseball over here have distinct colors that are different from the rest, which kind of shows us that in embedding space, these clusters are sort of put together in that way. So once we have this, for each image, we get a resultant embedding. And this pre-generated codebook that I just showed you before, we can essentially do this cosine similarity across a vast number of particles that can scale for a particle filter. And once we get this likelihood, The last part of it is just putting this together in a classical particle filter framework, which consists of the odometry information that you can get from kinematics, as well as the likelihood scores that we get from the learned model. And this can give us downstream tracking for a particle filter that we can nominally run at, say, 10 to 15 hertz for 50,000 particles that we operate with. And all of these are sort of SE3 poses that we're dealing with. To evaluate all of this, we collect a data set called the YCB slide data set, which consists of 50 simulated and real world trajectories with ground truth tracking as well. Here's another example of Midas Touch in action. Here, interacting with the YCB sugar box, we start out from a point. The tactile heat map here is agnostic of the history. It just tells us at a given point where it thinks the sensor might be. And we can see that we start out with a fairly wide spread of points with a multimodal distribution, and we can quickly converge to where we think we are just based on traversing edges and corners. Here's another example in simulation with us with the power drill, where we can see that we can converge pretty quickly, and it becomes a local tracking problem. The final part here is an interesting one, which is if you take a symmetric object with essentially a multimodal distribution that we form, where there are two antipodal pose candidates that can equally explain the trajectory that we have. What this ends up being is we end up with a pretty high error in pose, but we tend to treat this as a feature, not a bug, because both of them are reasonable candidates for this. But it's an interesting example to kind of showcase the multimodal nature of what we can capture. So in our code base that we have scripts for running this along with live interaction with them. We also have tools to generate this tactile data along with learning these image to 3D models and quickly getting into dirty laundry. Sim2Real is quite challenging, especially in the face of the discrepancies between simulated and real tactile images and the differences between interacting with triangular meshes and real objects. So closing the loop with real world fine tuning, such as differentiable filtering, is probably one way to go about this. Assuming contact episodes are continuous here is essentially when we break contact with things, the filter kind of acts funky in our case. So reasoning about something like a manifold particle filter, for example, that can handle contact and non-contact distributions better is one way to go. Finally, we kind of assume that for the purpose of benchmarking and really honing in on this, we've assumed that objects minimally move during these interactions, but we plan to relax all of these as we keep going. And the last part is that we don't really capture multi-contact data yet, which I believe is a far more interesting problem, but Midas Touch is a first step in that direction. But thank you. I'll be around to chat in the poster session. We have a small demo with a couple of YCB objects and the digit to play around with, but thank you.
Wonderful. So any questions? Yes, over there. I'll bring my microphone.
Thanks for the great talk. This is really cool work. Do you have any thoughts or comments on how you might apply a similar technique to localizing touch in deformable objects? For example, like seams of clothing or things like that?
Yeah, it's a good question that we often get as well. Like a lot of the assumptions here are just we work with these rigid bodies, but I think I think to an extent of rigidity, like we work with like paperboard and cardboard, it does work out fine, and we can assume that the objects are rigid. But I think the deformable object question is a bit more. It's in terms of when you have an elastomer sensor, we don't really know what is the interaction that's happening in those cases. So I think essentially assuming rigidity unless it fails and trusting the odometry is probably a good way to go about that.
Exploration strategies. Have you been thinking about how you move as well?
Yeah, that's another good question. Right now, everything I kind of showed you is kind of the passive perception problem. We're just doing random walks on meshes, and we're kind of just hand operating all of these. But I think using uncertainty information of the poses, for example, like in all of my visualizations, we have SE3 poses, but we also have like spatial uncertainty. I think an active SLAM type formulation for essentially minimizing exploration costs as well as minimizing uncertainty could be a way to go about this. There's also the question of coverage and exploration if you don't really know what the objects are, but there's a lot of things that you can chew down on in those directions.
We still have time for at least one more question. Yep.
Yeah, great connection between tactile perception and SLAM. So many people in the SLAM community these days are very excited about least squares optimization instead of particle filters. Did you consider, do you see pros and cons relative to your approach?
Yeah, that's a good question. A lot of the related work, in like local tracking problems versus like this is formulated more of like as a global localization problem. So the reason we ended up with a particle filter is just because of the multimodality of the data. So Gaussian assumptions and a least square framework is probably going to be good once you converge to a good mode of your pose. But just looking at like the multimodality of like, for example, when I showed you the mustard bottle, I think it's hard to capture those, and a particle filter kind of works well for those.
Yeah, you demonstrated nicely the multimodality. And I suppose you're going to be getting into mapping as well, novel objects?
Yeah, right now we assume that we know these objects and we can build these code books, but the goal down the line is to build these on the fly along with the optimization, which is a hard problem. Thank you.
Okay, yeah, thank you very much, Sudarshan. All right, so the third talk is titled Training Robots to Evaluate Robots, Example-Based Interactive Reward Functions for Policy Learning, and it's presented by Kun Huang. So Kun, over to you.
Yeah. Thank you for the introduction. Hello everyone, I'm Kun, a machine learning engineer at Cruise. I'm really excited today to present our paper, Training Robots to Evaluate Robots. This is a joint work done when I was at the University of Pennsylvania, together with Edward Hu and Professor Dinesh Jayaraman. I'd like to start the presentation with a very common real-world scenario where the task is to close and lock a door. It's a very simple task, and we just need to close the door, insert the key, and turn the key knob to lock it. But if you're like me, I always want to make sure that the door is locked by trying to reopen it. What's interesting here about this is that we are using physical interaction to uncover the true state of the door. In this talk, we are trying to answer, how do we teach a robot to achieve these kind of behaviors? But first, what's a typical way of specifying a task to a robot? Here's a common picture of a perception action loop, where perception produces state estimations, which then drive action decisions. In reinforcement learning, an engineer will usually write a dense reward function to specify a task, but this requires painstaking effort, and it must be repeated for every new task. To overcome this difficulty, one promising task specification framework is exemplary rewards. A human user can easily tell the robot what the task is merely by showing it image examples of what the environment should look like after a successful execution, such as images of locked doors, or in a different task, a water bottle with tightened cap. Then the robot performs RIL with the aim of altering the environment to generate observations that's similar to those examples. So here, perception happens not only during state estimation, but also during reward estimation. But is it always possible to reliably perceive this reward? The answer is no. Perceiving task reward is actually very hard in some cases. For example, in the door locking task we just talked about, lock and unlock doors looks the same. Or in the water bottle closing task, a tight and loose bottle cap are visually very similar to each other. In these partially observed settings, perceiving the task reward from passive visual observations is not possible. Instead, a human might try to open the door to check if it's locked, or turn the water bottle upside down to confirm that it does not leak. Based on this idea, we propose to train interactive reward function policies that can interactively evaluate task policy outcomes. Then the question becomes how to train this. Our solution involves replacing image snapshot examples with what we call actionable examples, real physical objects on which an agent can act. For example, it can be a physical door that the robot can open or close, or a water bottle that can be flipped upside down. Note that we get only the objects, not demonstrations, but we'll soon talk about how to learn this kind of disambiguating action policies. So now, instead of providing image examples of the success state, we provide actionable examples of success and train an interactive reward function policy, in short, ERF policy, to perceive the task reward. In other words, this is the policy that's going to learn to push the door or flip the water bottle to check for task completion. So how do you train the ERF policy? We already have possible examples of successful outcomes provided by the human user, such as locked doors. In addition to this, we will add negative examples, which are simply the outcomes of the current suboptimal task policy. Then the ERV policy is trained to interactively distinguish the positive examples from the negative examples. This is how the ERV policy learns good verification behavior. The final outcome of running the ERV policy is thus an automatically inferred reward. It is high only if the door is properly locked. This reward can now be used to improve the task policy. It encourages the task policy to actually lock the door, then simply push it into place. We call this final improved task policy the LERF task policy, short for learning from interactive reward functions. As a bonus, the IRF policy the ERV policy can even run at test time as an in-the-loop verification behavior. So basically, we will run the task policy until the ERV evaluation looks good. To recap our key idea in all of this, we train intermediate IL policies called ERV policies that provide rewards for training the final LERF task policies. Here are some examples of LERF on 3 different tasks. The first one is a simulated door locking task where the robot must rotate the latch into the locking position after closing the door, but the latch is behind the door and occluded so that locked and unlocked doors look the same. As we see here, LERF still manages to learn the correct behaviors. In the second task, the robot must build a stable tower with blocks of different weights, but it must leave the blocks to know their weights so that it can place the heaviest block as a bottom. Here we see that LERF learns to undo non-stable stacks once it identifies the heaviest block, which is visualized in green here. Finally, we also evaluate the LERF on a real robot screwing task in which the robot cannot observe whether the screw is tight or not without trying to twist it open. Once again, our method LERF learns correct screwing behaviors. Of course, we also evaluate our method quantitatively against several baselines. As all these tasks are designed to be partially observable, the baseline image-based exemplary reward method VICE performs poorly. On the other hand, our method LERF is able to solve all of them with significantly higher success rates. Furthermore, if we allow LERF to keep trying until the evaluation policy is happy, we can get a better performance. We even compared LERF to methods that have access to actual privileged information, like demonstrations, manually engineered verification behaviors, and ground truth state rewards. And we find that it performs on par or better than all of them. So it looks like the rewards provided by our interactive reward function policies did indeed produce good task policies. But what does the ERV policy do? It tries to open the door by pulling the door handle, pokes the bottom block to examine if the block stack is stable, and gently unscrews the valve to verify if it is tightened. Through these behaviors, the ERV policies are able to distinguish between success and failures. So we are excited about the performance of our algorithm LERF and plan to continue improving it. But one important current shortcoming is that the actionable examples can be cumbersome to provide. For example, we need to show the ERV policy around 100 physical examples of locked doors in the door locking task in order for the ERV policy to learn the actual verification behavior. One solution could be to train safe ERV policies that avoid destroying positive actionable examples. In conclusion, we have presented LERF, a framework for training example-based interactive reward function policies that evaluate task policies. And the ERV can provide rewards to train task policies and verify task policy execution in the loop in several partially observed tasks. Thank you all for listening. Happy to take any questions.
Thanks, Kun. So do we have any questions from the audience? Yes. Oh, there's someone coming that way.
What if I just add an arbitrary terminal like absorbing states? Then I just learned the perturbation function, perturbation policy to see whether it can stabilize that absorbing states. What does this like strawman compare to like learning a reward function? Is it necessary to learn this reward function?
I think that's a very good question. So I think your question is that what if we just learn a policy that perturb the terminal state of the task processing and see that if the state of the environment stays the same. I don't think that's a right assumption for all tasks around in real life. Like there are some tasks that are don't end in stable states, so that if you so that if you perturb it, it can change into other states. So here our method is not limited to stable terminal states.
I was talking about artificial like absorbing state. It may not be like visually the same state, because essentially you're also like playing with it to say like I just add the final states in the demonstration as this absorbing state. Will that do the same thing? It may not be the same state as the final state of the task, but it's the final state of the demonstration in your final stage.
Sorry, I think there's a misunderstanding here. So our method don't use demonstrations.
But you do have the actionable policy, and the actionable policy will end at one state, right?
Yes.
And if I just artificially add that as my absorbing state, and then I learn a perturbation policy, will that do the same, like serve the same job?
Can we talk about this offline?
Yes, definitely.
Sorry, I don't have an immediate answer right now.
Yeah, that's fine, no problem. I think we're gonna have to leave it there. Thank you very much, Kun, for your talk.
Thank you.
So that's all from me. I'm gonna hand over to my co-chair, Dinesh, for the rest of the remaining 3 talks.
Thanks, Ed. Thanks, Edward. Okay, so for our 4th talk of the session, we have Ilya Radoslavovich presenting real-world robot learning with masked visual pre-training. Ilya, whenever you're ready. Thank you.
All right, hello everyone. Today I will present our work on real-world robot learning with masked visual pre-training. So this is joint work with Peter Shao, Stephen James, Peter Abil, Jitendra Malik, and Trevor Darrell. So it's a really great time to be presenting a work on representation learning for robotics at this year's CoRL. So yesterday we've seen a wonderful tutorial by Professor Janet Bogg that has told us, has really set the scene for this work. And I won't go into the details on the related work and really the problems, but if you haven't seen the tutorial, I strongly encourage you to go online and see it. The one aspect of it I liked particularly was this poll where you, the CoRL audience, has sort of voted on what properties of visual representations you would want to see in something that might be good for robotics. And one thing that really came across is simplicity and compression. And these are really some of the main guiding principles that we've employed in designing our representations, as I hope the remainder of this talk will show. So the question we ask in this work is, can we design a single visual encoder that can serve many downstream robotic tasks? So intuitively, if I'm learning how to knit, I'm learning how to pick up cups, I'm learning how to drive a bicycle, I shouldn't need a specialist vision system for all of these. I should be able to use one general vision system that is able to adapt and enable learning these different tasks. And of course, this is a fairly natural idea. So why don't we have this yet? Well, of course, the devil is in the details. And the way we see this as having 3 core components to obtain these representations: the objective functions, the data, and the model. And these all have pairwise interactions, and I'll go through the specific design choices we made in this work. So first, we start with our objective, which is self-supervised learning through the masked autoencoder. So we build on the recent work from Kaiming He et al. The basic idea is, given an unlabeled image, we chop it up into patches, we mask out a random subset of this image, And then we use the visible patches to predict the remainder of this image. So the intuition here is that if a robot is able to mentally infill the gaps in the environment, it has probably learned something useful about the environment that should let it learn how to perform tasks in that environment. And arguably performing these tasks does require some notion, capturing some notion of objectness, object boundaries, and so on. And two really nice properties of this approach is that it does not use labels, so it's fully self-supervised, and it does not use data augmentation. So it does not have any form of strong assumptions that are hidden, which means that we can use this approach and we can deploy it to unlabeled data in the wild. So we do this by curating a really large data set that consists of egocentric videos from Epic Kitchens, Ego 4D, internet videos from 100 Days of Hand, something, and so on. So in total, we get a collection of 4.5 million frames that we use to learn these representations in a fully self-supervised manner. Of course, given the objective and the data, we also need an appropriate model that is able to consume this data. We use a transformer model that has been shown to be very successful in natural language processing and vision. So now we have these representations, and then given these representations, we want to learn policies that perform robotic tasks. So we do that by learning a policy per task by providing a small number of demonstrations for behavior cloning. I'll now go to our experiments and show the experiments we have performed. So first, we consider basic motor control tasks such as visual reaching, pushing, and picking objects. We also consider variations in scenes, visual generalization to things like toy fridge, where we move the fridge around, we randomize the fridge angle, and the task is to close the door. We also consider variations in objects, so picking up various fruits, bananas, apples, oranges, and so on. And we also consider variations in both scenes and objects where, for example, here, the task is to pick up a detergent bottle that is randomized across the sink. And then there are other distractor objects that are making this scene more visually complex. So quantitatively, our approach outperforms the existing vision models. So most notably, we outperformed the strong clip encoder that has been trained on 400 million language image pairs, which is far more data than what we use here, and might suggest that perhaps we don't need semantics as much for these robotic tasks, and perhaps some notion of spatial awareness and objectness might be more important here. Perhaps most excitingly, we observed that scaling our model leads to better results, but it's important to also scale the data, not only the model. And we see that when we scale both the model and the data appropriately, we get improvements in performance. And these improvements continue as we scale the model larger. So here we're showing performance on the y-axis, and the x-axis we show the size of the model, and we see that as the model gets larger, the performance gets better. And performance gains are larger for harder tasks. It's worth noting that our largest model, a VIT large, is a fairly large model. It is about 14 times larger than the ResNet 50 model, which is a commonly used visual backbone in robotics. We've seen that our representations are general in a sense that they can facilitate different robotic tasks, but can we use them for a different robot? So we performed a small case study where we try to apply this framework to a multi-finger hand. So the nice property of our approach is that it makes few domain-specific assumptions. So we take images as input, we compute these representations, and we output joint position angles as actions. So we apply the same sort of technique here that we previously used on a 7-DoF arm onto a 16-DoF multi-finger hand. But there is a small catch. How do we get demonstrations for this robot? One trick we do here is that we compute demonstrations using an Oculus VR headset. And of course, this type of demonstrations has been done before by other people, which is where the motivation comes in. But I want to highlight that we just use an off-the-shelf Oculus to compute these demonstrations. So in case you're curious or would like to collect demonstrations, this might be useful to you. But given these demonstrations, we performed various tasks such as visual reaching of different objects, as well as more complicated tasks such as flipping cubes, where the cube position is randomized across the palm of the hand. So our approach works, but of course it doesn't work always, and there are notable failure cases. So we observe failure cases where the object slips, the hand collides with the object before it manages to complete the task. We also observe failures in the multi-finger case where these are perhaps a little bit more interpretable, where the sort of if an object gets into a motion of a fingers, the whole trajectory would collide. And finally, I'd like to go back to the slide and really highlight that while we do have some favorable properties like simplicity, there is still a lot more to do, and there are a lot of more properties that we would like to incorporate in future representations. So in summary, we have the data, the objective, and the model, diverse in the wild data, self-supervision via the masked autoencoder and the large transformer. And perhaps this is a step towards a general model that can perform many different tasks. But of course, the proof is in the pudding. All of our checkpoints are available online. Please try them out. Let us know if they work, especially let us know if they don't work. And we'll see the community level SGD will converge to something that works eventually, hopefully. With that, thank you very much. And I would love to answer any questions.
Thank you, Ilya. Are there any questions from the audience?
Thank you for the great talk. I have a question about this visual generalization part. So do you have any language input to as a task specifications? Like, because you have this different object pickup, right? But you also have picking up same object in different contexts. But how do you differentiate when is the time that pick up different object and when is the time that you really pick up the same object? Thank you.
Thank you. So the basic idea is that we do not use language as task specification, and we train a policy per task. So we consider a single object picking to be a different task from the multi-object picking. So the task is implicit in the data that was used to train the control policy. So our motor control aspects are very much task specific, but our visual aspects are task agnostic and general.
So let's say if you're in a being, you have two objects, and then like you in the generalization testing, you switch the placement of two objects. Like how does the policy know is it about the spatial location you should reach to, or the same object you should pick up?
So the policy would capture the commonality that was present in the demonstrations provided by the human. So it would be up to the human to determine what the task is.
Okay, thank you.
That's unfortunately all that we have time for. Thank you, Ilya.
Thank you.
And for the next paper, we have Ashish Kumar presenting legged locomotion in challenging terrains using egocentric vision.
All right. Hello, everyone. I'm Ashish Kumar. And today I'll talk about legged locomotion in challenging terrains using egocentric vision. So in the recent years, we have seen a lot of these legged robots that can walk on a very diverse set of challenging terrains. On the left-hand side, we have our own robot from RSS last year. But what's interesting about all of these robots is that they're completely blind. So this begs the question that do we even need vision for walking? Or we can rephrase it to ask, what can vision additionally buy us over what we already have? Well, vision can enable intentional and precise foot motion and can let you cross gaps, stepping stones, stairs, and other such challenging terrains. And the focus of this work is to enable legged robots to cross all of these terrains. So how do we use vision? The typical approach is to use vision by completely decoupling it from control. And the vision is first used to build a detailed terrain map, which requires precise pose estimates in the real world, which are very hard to obtain reliably during deployment in the real world. And this leads to very noisy terrain maps as a result. Now, methods which use vision via the bottleneck of these terrain maps are fundamentally limited in how much they can perceive of the terrain around them. And this prevents them from achieving very precise and accurate foot placement, despite having vision. So the original problem we set out to solve still gets unsolved, even though we have vision in the loop. So in this work, we asked the question that do we really need terrain maps? We hypothesize that we don't, and instead we tightly couple vision and control without the use of maps in the middle. And let's see what can such a system do. So here we only have an egocentric camera, and you can see the camera feed on the top right, and all the compute is on board. And it's directly going from perception to control. And we see that it can do these stepping stones, which have variation in the different arrangement of stools. So all of this was just set up in my living room, no motion capture, no maps. It experiences this gap and it's able to cross this reliably as well. So here are some staircases. And if you look closely, these stairs are quite high compared to the height of the robot. So they're high and they're also uneven even within a single staircase. So if you look here, this stair is almost as high as the robot. So our robot struggles a bit, but it is able to manage on these ones. And we can take this and test out on all the other stairs that we found around at CMU and Berkeley. Here is a large rock, completely uneven, that the robot is trying to get on, and a very sharp dip that the robot has to cross to get back down. And here, if you notice, the foothold of the robot is extremely unstable because the ground consists of loose mud. So it has to struggle multiple times repeatedly before it is able to make it to the top. And this step is also as high as the robot, and it takes multiple attempts to climb it, but it is able to get on top of it. And this is an unstructured abandoned site, which we did not simulate in simulation. We did not train our method to look at this, but it is able to work on this even though it has never seen this before. So how do we do this? We'll first solve the problem in simulation where we have access to everything that we would need for walking. So we want to learn a neural network that can take the observation and it can predict the action, which is the target joint angles at 50 Hertz. But we want our system to be aware of the terrain around it. So we will take a local snapshot of the terrain around the robot, compress that into a latent vector and feed this terrain vector into the policy. And we will also take all the physics parameters like friction and payload and feed that into the policy as well. So we have a policy which is aware of its visual surrounding, and it is also adaptive because it knows the friction, payload, and other things it's dealing with. So we train this end-to-end in simulation using PPO and Isaac Gym. And our reward function is just to track velocity and minimize energy. We do not use any predefined gates, foot tapping motions, or reference motions, and let realistic walking gates emerge purely from the constraint of energy minimization. We simulate a diversity of terrains in simulation. And at the end of the training, we have a realistic walking gate, which can walk on all of these different terrains that we have. If we try to deploy this in the real world, the problem is that we cannot directly measure any of this privileged information in the real world. But what we can do is we can go back in simulation and distill this policy into another one, which knows how to operate from the onboard sensing. So we will use the egocentric depth to predict the terrain latent, and we will use the proprioception history to predict the physics parameters. And we can train this in simulation itself because we have access to the ground truth latents, and we can also render the onboard sensors in simulation as well. So we train this using supervised learning, and now we are ready to go. So let's first take it on stairs, and note that these stairs are designed for a human height, and our robot is smaller than a human, but it is also smaller than all the other robots that you might have seen around. And this makes it very difficult to climb on stairs because using any heuristic gate, because there is just not enough clearance to under the robot to fold its leg. While going down, it becomes even more sharp and steep. Let's see what our robot does when presented with these stairs. So it's interesting to note that it has learned this emergent hip abduction behavior. So it flexes its hip to the right one to the right and left one to the left. So it opens it outwards to be able to climb these stairs. And this happens because we do not use any predefined gates and just let reinforcement learning figure out the right gate automatically. We can also put this on these stepping stones, these tools that I just set up. And we see that it critically needs this precise foot placement to avoid gaps and irregular stepping stones. And this emerges without ever using any maps or planning in the loop. And we can take our system, and we took our system and deployed it at most of the places that we could find around in Berkeley and around in CMU. And our approach is map free and gate free, and we can just take it anywhere and just deploy it simply. So now let's try to quantitatively understand how well it works compared to baselines. So we compare it to a blind policy which does not have vision, and we compare it to a mapping-based method which builds an intermediate map before it can go to actions. On slopes, we see the performance is similar. So we are measuring the average distance that it can walk in 20 seconds, and we do this in simulation over a large number of seats. We see that it is roughly similar for slopes, but the moment we get to stepping stones, we observe that the blind and map-based are about the same. So the noise that is added in the maps to simulate noisy terrains in simulation ends up killing all the information there is for precise foot placement. And the gap between this and our method is huge, and our method performs significantly better. We see that the terrain holds on this trend holds on other terrains as well. And if you notice, our method is better than the baselines, but it's still not perfect. So here are two of our failure cases. On the left, you see that the robot falls down because it just cannot see, is unable to estimate the dip in front of the robot. On the right is a planning failure. So we ran this 16 times, each time with a different configuration of stools. And in one of these setups, you can see that the leg ends up stepping into a hole as opposed to on a stool, and it just falls down. And since our robot requires no map and no gates, we can simply carry it with us. So here is Ananya operating the robot, and you can just see it right here. One interesting thing about the robot is that in the transit, the front camera broke, so it doesn't work anymore. So we put a new camera on it, and we fine-tuned it overnight to get this to walk. But now it can walk again on stairs. Thank you, and I'll be happy to take any questions.
Thank you, Ashish and Ananya, for the wonderful demo. Questions from the audience?
Yeah, thanks for the great talk and very impressive demo. One question I have is on the robustness of this vision-based controller. So by adding another modality into the controller, that could also be another avenue for noise to seep into the system. Have you considered like evaluating this in environments where like maybe the vision might experience a lot of noise like fog, sand, and would you expect this controller to still do well by operating over the appropriate set of input? Thank you.
So is your question that on things like sand where the vision might fail, will the controller still work?
Yeah, I mean, just in some scenario. Yeah.
So as you notice, this version of the robot is built on a blind version of the robot that we had last year. And that robot we tested on sand, on mattresses, on grass, on all of these different terrains, and some rocky surfaces and watery surfaces as well. So it still has that fundamental proprioceptive reflex where if it is trying to walk and it is not able to, it will adjust its gait based on proprioception. So if you saw, one of the arguments was about these physics parameters, and on the sand, you could think of it as a deformable object. On a slippery surface such as snow, or for example, we saw the version where it was trying to climb a slope, but it was all muddy. And so in those cases where the visual system might not be as good, it would rely on proprioception to continue walking.
Here's an online question. The distillation process uses supervised learning, which I believe is behavior cloning. If so, how did you avoid the distribution shift that typically occurs with behavior cloning in long horizon tasks?
Thank you for the question. So we use Dagger, which is a variant of behavior cloning. So we start from a policy which works not that great. So this is the final deployment policy. We unroll it in simulation. We go back and take the phase 1 policy to relabel every step. And then we train on this. So this gets around the problem of distribution shift seen in behavior cloning.
All right, that's about all that we have time for. Thank you, Ashish. So our next speaker is Atanas Mirchev, and the paper is titled Prism, Probabilistic Real-Time Inference in Spatial Models.
come on. Okay. Alrighty. Hi, everybody. So my name is Athanas. I'm a member of the Machine Learning Research Lab in Munich, Germany. And today I'm going to talk about PRISM, which is a method for spatial inference, specifically in spatial world models. And this is done by me and colleagues. As I said, we are part of Volkswagen AG. So what is a spatial world model to us? By a spatial world model, we generally mean a probabilistic generative model that can predict agent motion and visual perception as well. And we care about these models because we want to enable long-term planning. So it's not just about controlling an agent with a low-level control and so on, but we, sorry, yeah, okay, good. But we also care about the models for high-level control, long-term planning, imagining what would happen into the future once the agent starts moving around, what it's going to see, how it's going to move in full 6 degrees of freedom with rendering enabled and so on. And this is more important for establishing high-level goals, etc. And this demands some level of fidelity of the model that you infer from data. And what we care about is that the model really can capture images, really can render from novel viewpoints, and can really predict the agent movement well. We also want the model to be probabilistic, meaning that we want full posterior estimates for all of the variables we care about, because we want to be robust towards model errors, also towards system noise, and we also want to enable information theoretic intrinsic motivation rewards for downstream tasks like the exploration in such a model. And we want them to be fast, right? So that's self-explanatory because we want to do control in such models. What I'm going to focus on today is how to infer such models from data in a reliable manner that satisfies all of these 3 requirements. And to understand how we do this, first I need to introduce our paradigm of choice, which is working with state space models, and these are augmented with a map. So in such state space models, we have variables, we have observations over time, which are RGBD data, then we have states over time, which are poses and velocities, controls, which are accelerations, and a map, which is a volumetric map representation, and the states in the map are latent variables. In such models, we define differentiable rendering emissions, which are basically telling us how to reconstruct observations from given a map and a camera pose. We shoot rates into the scene. It's similar to how NERF does it. Our renderer is slightly different for efficiency reasons. I'm going to explain that later. And we also have the transition, which models rigid body kinematics, which tells us how the agent is going to move if we condition it on control inputs. These 2 together give us this effectively very expressive predictive distribution that tells us what's going to happen into the future, right? And based on it, we can establish controls, rewards based on the images, for example, that the agent would perceive, which is not trivial to do otherwise. But we have a problem. To infer such models, we really need to reconcile rendering, uncertainty, and speed. And this is not trivial because rendering in general is quite expensive. Like if you look at NERV, even the latest developments still are pushing the envelope a little bit in terms of what you can do. And they're only doing point estimates for the maps that you obtain. And on top of that, we want uncertainty, right? So uncertainty usually implies, if done with gradient descent, some sort of stochastic optimization, for example, through the variational lower bound, like the elbow. And if you consider this in our state space model, and especially for smoothing posterior, you'll quickly notice that this gets very unwieldy. We have many time steps for which rendering needs to be executed, and we need to propagate gradients back, and we need to do this under the noise of the approximate posterior that we are estimating, which is challenging. So the solution we propose to this is to actually do inference of the filters and not smoother. And we consciously accept all of the biases that come with a filtering solution, right? So filters can possibly drift if they make errors that they cannot revisit, etc. But why we do filtering is because it's recursive, and recursive means we can focus on the individual filtering steps, one at a time, basically divide and conquer. And we can also apply one-shot updates, closed form updates, instead of having to propagate constantly through the renderer and do gradient descent through it. We maintain 2 filters, one over the map and one over the state, 2 marginal filters. We don't do the joint because the joint would require too much memory because the map is huge. It's a volumetric grid representation. Even if it would be a neural map, it would still be too big to do properly. But all we know, these filters, like the 2 marginal filters that we maintain, still interact with each other. And I'm going to try to explain to you how by just giving you a glimpse into our derivations. So what we care about is to derive these filters properly from the generative model. So we step on this simple Bayes recursive equation, which is for the Bayes filter for the joint of the map and the state. To get the marginals, we will just marginalize the relevant variable out of this one. And then here you can see the recursion, right, that I was talking about, which is a standard fair with filters. And what the first big approximation we make is that we substitute the previous filter of the map and previous state with our two marginal estimates from the last time step, because that's all we have due to computational constraints. And then we have the transition emission, like prediction, update step, whatever you want to call them, right? And the other big approximation that we do here is we replace all of the resulting integrals with one sample Monte Carlo approximations for speed. These two approximations are quite crude, but they're leading us to a pragmatic algorithm that can still work and give us some uncertainty estimates, which are still good, and preserve the rendering and the real time. The method breakdown then is rather straightforward. So after we do all of these derivations, we get 4 steps. We update the map in closed form, we render from the map, then we optimize for a pose with maximal posteriori objective. Then we do a Laplace approximation to get state uncertainty for the pose. And then we have a linear Gaussian system update to get velocity uncertainty and fuse the state estimates of pose and velocity. So overall, our main contribution is just identifying where these traditional techniques fit in a filtering paradigm and how they can be derived from it. We also really signpost all the approximations we make so that it's explicitly clear what we're missing by doing this. And we have a comfortable runtime of under 100 milliseconds per update step. So now getting to the filters themselves, first the map filter, the form that we obtain after derivation looks like this. So on the top line, you have a map update multiplied by previous map belief. If those are Gaussian, which are in our case, then this is very fast. It can be done in closed form. And the derivation here is very similar to what Grisetti et al. Did in 2005 for 2D mapping. We just do it for 3D now. One property of our renderer, as I said, is slightly different from NeRFs, is that we can actually use closed form SDF updates and their probabilistic interpretation to get the map updated with uncertainty. And then mapping looks like a little bit like the video on the top right. So if you do it with given poses. So the main property here is that this map update is very fast to evaluate. It takes 9 milliseconds to just run it compared to gradient descent through the renderer, which would take much, much longer to get the same visual fidelity. For the state filter, the derivation is similar. It's slightly more complex, so I'm just going to use placeholders to explain to you how the last step is done. The state filter comes down to multiplying 3 terms, a log likelihood term, which is our renderer, a pose prior, and a velocity term, which is velocity given a pose. These conditionals need to be combined in a principled way. So the first thing we do is we do maximal posteriori optimization of the first 2 terms. We get a pose for the agent, which is a point estimate. We do a Laplace approximation over it to get uncertainty. And then we have QZ pose, which is a full Gaussian distribution over the pose. We fuse this together with the velocity given pose, linear conditional, and this gives us a linear Gaussian system, which we solve to get the joint posterior. The evaluation that we do is on UROC, Blackbird, 2MAR-GBD, and we pretty much show that the method works. It's similar in quality and localization to all of the other baselines that we consider. It works as you see on the video. And coming to the limitations, we have some approximate assumptions, as I said. So replacing this joint conditional, joint posterior with 2 marginals, 1 sample Monte Carlo, etc. These, in fact, have an implication on how the uncertainty is calibrated. So for the state filter, for example, we can see that Prism is slightly pessimistic. So it's curved and not following the diagonal, which will be the optimal solution. Dynamic maps have remained out of scope. Neural maps have remained out of scope, etc. So if you're interested in this and you find it useful, come talk to me during the poster sessions. Ask me questions now. Happy to hear them.
Thank you, Atanas. Questions from the audience. I see one hand up here, and we might have time for just about one question.
Hi, thanks for the talk. Yeah. I was wondering, like, if I'm not mainly interested in computational speed, but rather in accuracy, does it help to improve the number of Monte Carlo samples? Did you evaluate that?
Can you repeat the last part?
Does it help to give more Monte Carlo samples to the method? for the trade of computation versus accuracy?
Yeah, sure. I mean, in general, all of the approximations we make lead to some loss in terms of accuracy that you can compensate for by drawing multiple Monte Carlo samples or relaxing uncertainty propagation assumptions to get it better. The point is that this is the only way we see right now, which gives us a fully probabilistic solution for with a differentiable renderer such that you can get this rich model. Yeah.
Okay, thanks.
All right, I'd like to thank all the speakers for the excellent talks and for the great work. And thank you all the audience.